В этом отношении похож на Дэвида Мамфорда, который тоже с детства был миллионер. Он, правда, работал в Гарварде всю жизнь, но получал зарплату $1. Дэвид Мамфорд, такой великий алгебраический геометр, философский лауреат, ученик Гротендика. А Макдональд даже нигде не работал. Но мне повезло, я увидел живьем. Ну, так он такой невзрачный, в отличие от Мамфорда. Мамфорд породистый, высокий, бородатый, красивый. Мамфорд еще известен тем, что когда Миша Вербицкий... А, впрочем, может, вы не знаете Мишу Вербицкого? Или знаете? Ну вот, когда он учился в Гарварде, то там все в Гарварде, аспиранты, обязаны проходить такую педагогическую практику и преподавать, вести курсы у студентов. И сначала аспирант ходит на лекции профессора Мамфорда, например, и смотрит, значит, как тот ведет эти лекции. Потом он готовится и читает свою пробную лекцию, и с ним разбирают, значит, руководящие товарищи его ошибки, и он после этого начинает преподавать самостоятельно. И Вербицкий у Мамфорда, значит, на курсе дифференциальных уравнений все это проделывал, и его пробная лекция выпала на тему линейные дифференциальные уравнения, такие вот, которые в сущности сводятся к обращению матриц. Значит, он для примера решил разобрать там всего порядка 2, то есть 2 на 2 матрицы. Но чтобы это выглядело аутентично, он не обратил матрицу заранее, а стал обращать ее прямо на уроке. И, значит, все 1,5 часа оказались заняты бесплодными попытками обратить эту одну единственную 2 на 2 матрицу. И, значит, после этого Мамфорд на него орал так, что прямо там стекла дрожали, а ему запретили преподавать, и он... Нет, сейчас Вербицкий читает лекции хорошо, но вот та лекция была просто... Я понимаю, что он в Бразилии, да, но та лекция была просто такая фантастическая. Хорошо. Значит, что, мы доказывали теорему, давайте ее опять сформулируем и продолжим доказывать. Но мы говорим про алгебру Холла, и я уже не буду напоминать, что такое алгебра Холла, unless you request explicitly. Ну, хорошо. Значит, есть О, это либо ZP, или там его расширение, либо FQ, ряды Тейлора. Есть категория конечных О-модулей. Дальше алгебра Холла имеет базис классов изоморфизма этих О-модулей. Значит, у лямбда это модуль типа лямбда. Все неразложимые модули нумеруются натуральными числами, а все классы изоморфизма — это вот какие-то суммы с кратностями, то есть разбиение. А умножение здесь у μ умножить на у μ равно сумма g большое лямбда μ от О умножить на у лямбда, где g лямбда μ большое от О — это число таких подмодулей типа νu и котипа. То есть это тип-фактор модуля. μ в модуле типа лямбда. Окей? Я ответил, Всеволод, на ваш вопрос. Вот изучая, значит, вот теперь теорема 2, знаменитая и неприступная, говорит, что существуют универсальные многочлены G, лямбда, μ, ню от T с целыми коэффициентами, такие, что эти структурные константы равны специализациям этих многочленов при t равном q. А q — это число элементов в поле вычетов. Это первая часть. Вторая часть гласит, что степень этих многочленов не больше, чем n от лямбда минус n от μ минус n от ню. Но теперь в отместку, Всеволод, вы сами мне скажите, что такое n от лямбда.
Сейчас n от лямбда — это у нас сумма у и, это и минус 1 на лямбда.
Да. Спасибо. И, наконец, последнее утверждение, что коэффициент при этой априори старшей степени равен коэффициенту Литлвуда-Ричардсона c лямбда μ ню. Структурные константы умножения в базисе из функции Шура. То есть эти у лямбды, они как бы, ну там вот с точностью до, может быть, каких-то перенормировок, они являются деформациями функции Шура. Хорошо, и мы значит, давно уже неделю, нет, больше, находимся в процессе доказательства этой теоремы. Ну, в общем, да, особенно первый. Первым точно доказали. Значит, мы сформулировали предложение 3, которое говорит, что да, я... Да. Мне неохота много говорить про массивы еще раз. Но, тем не менее, там была какая-то статистика, значит, были массивы. Это как бы наборы, ну, не знаю, композиции с заполнением числами. Это такой аналог полустандартных таблиц. Обобщение полустандартных таблиц. Значит, утверждалось, что у каждого массива А есть некоторая статистика D от А. Ну, и я не буду сейчас напоминать, как она определяется. И утверждалось, что А лямбда μ — это сумма по всем массивам, Q в степени — это статистика, а массивы берутся строго упорядоченные по строкам формы μ и веса лямбда транспонированная. Вот. Теперь что такое а лямбда мю еще? А лямбда мю это вот что такое. А лямбда мю такой, как сказать, частный случай этих самых структурных констант. Но только структурных констант от многих переменных. Здесь лямбда, а здесь будет там μ1 и так далее. А именно, это число флагов m равно m0, но и он при m с одной стороны равен m0, а с другой стороны он равен m лямбда, он типа лямбда. Здесь m1, m2 и так далее. Здесь ms какой-то нулевой. И сейчас, прошу прощения, он не m лямбда, а m мю наоборот. Значит, тип объемлющего модуля равен мю, а тип m итого, m минус первого фактора по m итому равен 1 в степени лямбда транспонированной ит. То есть такой элементарный модуль. То есть мы рассматриваем такие образующие в, не знаю, RT. Это класс вот этого самого модуля. Значит, вот такой нулевой модуль, ну, длины R. Или, скажем, если мы над полем FQ, то где? Да, вот там. То размерности R над FQ. Нулевой модуль. Он еще называется элементарным, да, там, где Z или P действует нулем. Вот. И вот мы смотрим такие флаги. And this is a lambda mu. The claim is that this number of flags, and it's clear, well, maybe mu has to be here, and this has to be lambda 1 transposed, lambda 2 transposed, and so on. So it's a, well, no, again wrong. 1 to the power lambda 1 transposed, 1 to the power lambda 2 transposed, and so on. So when we multiply very particular elementary modules, then the corresponding structure constants in the whole algebra are called A lambda mu, and there is an explicit counting formula for them. And this is apparently polynomial. Okay, so this was yeah, our proposition 3, and it was not proved last time, but we only derived part one of theorem 2. So last time, we derived from proposition 3 theorem 2 part 1. Okay, and also we formulated proposition 4. Namely, that the degree of this polynomial a lambda mu of t. I mean, well, a lambda mu as well as formulated here is just a number, but this number depends on q, and we proved that this dependence on q is polynomial. So for this reason, I mean that a lambda mu is a polynomial with positive integral coefficients in variable t. Well, there it's q, but we can specialize t equal q. So degree of this polynomial is at most n of mu minus n of lambda. We proved this, namely we derived it from certain lemma number 5. And this lemma was about sum counting. And maybe I will not formulate once again, but we proved it as well. Last time. So we proved proposition 4 as well. And so if you have module M and an exact sequence, 0, whatever, n, m, l, 0, then the cotype of n in M is, by definition, the type of the quotient L. Okay, so this was the end of the last time, and so as you see, we still did not prove second and third parts of theorem 2. I mean, we didn't even derive them from proposition 3, which we didn't prove either. So nothing is proved. But at least we can make some definition, and it's a renormalization. A lambda mu of t tilde, this tilde, is defined as t to the power n of mu minus n of lambda, a lambda mu of t inverse. So we know already that this degree is not too big. So you see that this lies in, it's actually polynomial. It looks like maybe a Laurent polynomial, but due to proposition 4, it's actually a polynomial. And moreover, since it's just counts things, it is a polynomial with positive, non-negative coefficients. Okay? And corollary of lemma 5 is that this polynomial counts certain statistics d tilde of A. So the sum is over all arrays of shape mu, weight lambda transposed, and strictly row ordered. And here, d tilde of A is the cardinality of the following set. We have pairs of boxes in our diagram, our shape, mu, such that the filling of x is less than the filling of y and is less than the filling of x right. So anyway, a of x is less than a of x right, but by the definition of strictly row-ordered array. But a of y must be in between. Okay, and well, sorry. Let me continue here. Is still the statement of corollary. That a tilde lambda mu of 0 is, pardon me?
What is the difference between d with tilde and d without tilde?
In d without tilde, I think we had a non-strict in. No. There was an extra condition that y was lexicographically smaller than x. Okay, so, pardon me? This? We counted the leading coefficient last time, as far as I remember.
Можно посчитать те диаграммы, в которых d tilde от a равно нулю. Точнее, те массивы.
Yeah. So in this lemma, we proved that d tilde of A vanishes if and only if A is, so well, lemma 5 part C said that d tilde of A is 0 if and only if A is column ordered. Okay, so this count. Pardon me? Right. And there was no part C. Thank you. All right. Okay. Fine. So this was a quick recap. And now we deduce theorem 3 from, three parts, sorry, theorem 2 parts 2 and 3 from proposition 3. Okay, so we consider a free lambda of t module. I'm sorry. Z of t module, lambda of t with basis E lambda. Okay. Now the matrix A tilde lambda mu of T is strictly upper triangular. I mean, with respect to the dominating order. So we already proved and used it for A lambda mu without tilde, but A lambda mu with tilde is just a certain renormalization. So if, well, A lambda mu equals 0, if and only if A tilde lambda mu equals 0. And A lambda mu equals 1, I mean, as a polynomial. If and only if A tilde lambda mu equals 1. Just we flipped and yeah. No, we flipped and shifted. So it's a symmetry with respect to certain axes. It doesn't matter. We just take a symmetry with at a certain point, not at 0 point, but at a certain point. But okay, so this matrix is strictly upper triangular, hence invertible. Okay, and now we can consider a system of equations. E lambda transposed equals the sum over mu A tilde lambda mu of T P mu of xt. Well, this of x. So these are certain indeterminates. Well, they are elements of lambda of T, so they are symmetric polynomials in X with coefficients in T, and there's a system of equations on them. But this matrix is invertible, so this system of equations has a unique solution. And starting from next time, we will study those guys. These are called exactly whole Littlewood polynomials. Okay, so this will be the main topic for the rest of March. But so far, we're only using them as a black box. They just exist. We don't know anything about them. But they do form certain bases in here, because they differ from the elementary symmetric basis by some invertible matrix. Just because it's strictly upper triangular. If lambda equals mu, then it's 1 on the diagonal. If lambda is less than mu, it's 0. Or I should say it's 0 unless lambda is bigger than mu. Yeah, bigger or equal than mu. So a basis in this deformed symmetric functions ring. Fine. And now we define the structure constants. F, so P mu times p nu equals the sum over all lambda f lambda mu nu of t p lambda. Just in this new basis, we consider the structure constants of the usual multiplication. And so these guys are certain polynomials in T. Now, just by construction, pardon me? Why do they form a basis? Just because you know that the elementary symmetric polynomials do form a basis. Huh? Over yes, over z of t, over lambda of t. Yeah, they.
So we consider this not over z but over z of t.
What is the extent scalars from z to z of t? You know that in the usual lambda elementary symmetric polynomials do form a basis. Now we extend scalars, they still do form a basis, and they apply some invertible matrix, so you obtain some new basis of whole Littlewood polynomials. And now you write down structure constants in this basis, but the things we were interested in are almost the same. I mean, there was another basis like u lambda, yeah, and the transition matrix from the elementary symmetric to u lambda was given by a without tilde. So the only difference is now that the transition matrix is tilted. Yeah, for the basis u lambda, we used a lambda mu. For the basis p, whole Littlewood basis, we use a tilde lambda mu. The transition matrices are just a little bit renormalized. And it results in that the structure constants are also renormalized. F lambda mu nu are renormalized g lambda mu nu, namely g lambda mu nu of t equals t to the power n of lambda minus n of mu minus n of nu times f lambda mu nu of t inverse. Okay, but we already do know that these are polynomials. This much we proved already. Yes, the first part of the first claim of theorem already deduced. Just because the
Мы просто сказали, что это у нас будет реформализация h, и дальше с точностью до умножения на t.
Yeah, so we know that E like there, and now you just rewrite your multiplication in this basis or in basis p, and consider the structure constants.
То есть мы говорим, что у нас...
So the statements that u mu is the sum of g lambda mu of t u lambda and this and that they are mutually consistent. And you can check them this yourself at a better occasion. Huh? How do you mean? What do you mean by this? There is a whole little woods are obtained from elementary symmetric by application of this matrix A lambda mu tilde inverse. Well, certain composition of matrices. I mean, if t equals 0, I will just say it in a moment. If t equals 0, then indeed whole little wood polynomial specialized to Schur functions. We'll just see it in a moment. Okay?
Вопрос по тому, как именно это проверять, то есть по общей идее. То есть правильно ли я понимаю, что...
But you just plug in the formula.
То есть мы подставляем вот, в произведение.
Mm-hmm.
Сейчас. Нет. То есть предлагается нормализовать вот это произведение слева. То есть мы, как говоря, можем вместо ушки выразить через
Yeah?
дальше подставить их сюда и дальше
Yes.
написать.
Yes. Okay. So indeed, as we just discussed, if we specialize t to 0, we get just Schur function S lambda. So why this is so? Why this is so? Because where were we? There. A tilde lambda mu is k mu transposed lambda transposed. And this is the transition matrix from Schur functions to elementary symmetric. Yeah. Okay, so we know this much, and then it follows that the structure constants at 0 are the same as structure constants of multiplication in the base of Schur functions. C lambda mu mu. Okay, so at some point, maybe in the end of March, I will prove well some little Richardson theorem, which gives some combinatorial explicit count for these coefficients. I mentioned this many times already, but so far we are using them as black box, but they make some interesting sense, and I will talk more about it. Fine. So from this, we see that the degree of G lambda mu nu must be at most n of lambda minus n of mu minus n of nu, just from this formula. And the leading coefficient, a priori leading coefficients, equals C lambda mu nu. And that is what we wanted to prove. So we finally succeeded in deducing theorem 2 from proposition 3. Okay? But proposition 3 is yet unproved. So now we move to its proof. Maybe let me erase this logic. To prove proposition 3. And now we define a certain relation. We say that a composition beta is a little bit smaller than alpha, and we write beta, I forgot the name of this symbol. If no, I mean in tech, I forgot its name in tech. So if for any I, alpha I minus 1 is between beta I and, well, beta I is between alpha I and alpha I minus 1. This was first thing. And the second thing is that the distance between alpha and beta is defined as the number of pairs I, j, such that beta I is equal to alpha I, and beta j is alpha j minus 1, and j alpha j is lexicographically less than I alpha I. Okay, and this horrible notation is ij is lexicographically less than I prime j prime if j is less than j prime or j is equal to j prime, but I is bigger than I prime. Okay, so this is the end of this definition. And now lemma 7. Did we have corollary 7? Corollary 6? Don't see corollary 6. That's the life. No. Maybe I just erased it. I think maybe I erased it.
The corollary 6 was of, I think, lemma 5.
Right. So I just erased it. Okay. Well, but Anik knows that there is corollary 6. So lemma 7 says given compositions alpha and beta such that beta has length r, so beta I vanishes for I bigger than r. Then the set of arrays of shape alpha, weight beta, strictly row ordered, is in bijection with the set of flags, if I am allowed to say so, alpha 0, alpha 1, and so on, alpha r. R is the length, well, a priori length of beta, such that 0 equals alpha 0, a little bit smaller than alpha 1, a little bit smaller than alpha 2, and so on, and a little bit smaller than alpha r, which is just alpha. And the total size of alpha I minus the total size of alpha I minus 1 is exactly beta I for any I. And finally, the statistics d of a, which I neglected to recall in the beginning of today's class, corresponds under this bijection to the sum over all I of the distances between alpha I and alpha I minus 1. Okay, so this lemma has a rather long statement. That's a good point. But what should I erase? Maybe this. No? The top part. Okay, let me erase the top part. Yeah, so the statement of this lemma is unusually long, but for reconciliation, its proof is unusually short. as Kirill mentioned, the proof is just this bijection. So an array A goes to the flag A alpha I, where alpha I is just the preimage of this subset from 1 to I, of this segment from 1 to I. So array is a map from alpha to positive integers, right? Some filling. And then you can check that indeed the statistics D goes, which I didn't recall anyway, goes just to the sum of distances. But it's just from definition of the statistics. Yes? Yes? Okay. And now finally, proposition 3, which is here. Yeah. Proposition 3, it's for counting of flags. Yeah, that the certain count of flags is given by universal polynomials. Yeah, and we discussed, what was it, a week ago or more, that some very stupid, some baby example of this is for just Grassmannians. Yeah, if our whole algebra is not for models over O, but just for models over finite field FQ, so just for vector spaces, then we just count points in Grassmannians. Or maybe in flags, if we're interested in long flags, not just two-step flags, but many-step flags. When we have to count points in flags, and this count follows by induction from proposition 8, which is just one step of induction. So assume lambda is mu plus r, just one number r. And alpha is a composition which is equivalent to partition lambda. Just by renumbering its parts, we obtain partition lambda. Then the structure constant, g lambda mu 1 to the power r of O is equal to the sum over beta that is a little bit smaller than alpha, q to the distance from alpha to beta. And the sum is taken over compositions beta that are equivalent to conjugate to mu and smaller, a little bit smaller than alpha. And you see that here we count flags where the associated graded is elementary. Yeah, and here we just assume that the submodule is elementary and the quotient is arbitrary. But then we'll go on like this. Inside this quotient, we'll take elementary submodule and so on and so on. So if we know this and we apply it many times, we obtain some formula for counting flags with elementary associated graded. Dash V, what? Like this? Thank you. And what is the meaning of V, I wonder? Vertical. Dash and vertical. Okay. And V dash would be to the left. Okay. Great. Okay, so the proof here. Let M be a model of type lambda. Then the desired structure constant is the count of submodules n inside M of type 1 to the R, elementary, and cotype mu. So in other words, equivalently, n is an R-dimensional FQ vector subspace in the circle over M. Circle is just the union of all elementary submodules. Well, N is an elementary submodule, so it lies in the circle. And by definition, it has length R. Maybe let's call it S. So in other words, N lies in the Grassmannian overfield FQ of R in the vector space S. The dimension R subspace in the vector space S. And we know that this Grassmannian over any field at all, in particular over finite field, is the union of Schubert cells. Well, most, what can I erase now? Maybe this. We will not need, in fact, anything at all. We're ready to finish our proof. Yeah, so you had this in your home assignment, and most of you solved it, but let me recall the solution and also reformulate it in some other words more suitable here. So just a recap of Schubert cells. So choose a basis, Vi, in S, then the Schubert cells are indexed by the subsets J in this set I with cardinality R. Namely, Xj is it's a cell, so it's an affine space with coordinates Cij in Fq, where J is an index in capital J, and I is an index in the complement, which is bigger than J. Namely, the collection Cij goes to a subspace with basis Vj plus the sum over I C I J V I over all J. Then the dimension of a Schubert cell is something, and the number of points is q to this dimension. So the number of points xj is q to the power d of j, where d of j equals, by definition, the cardinality of set of pairs ij such that j is in our index set, I is in the complement, and I is bigger than j. Okay, so this was a recap about Schubert cells. So we know that the number of points in Grassmannian is just the sum over all j, q to the power d of j. And we only have to relate this count to the desired count. Okay, so now, well, we have to somehow compute explicitly the circle of model M, right? And write M in terms of generators, just the sum of cyclic modules. And the length of these modules are alpha I. And we set I is the set of indices I such that alpha I is positive, and Vi, the base is like upstairs, is pi to alpha I minus 1 xi, where pi is a uniformizer, that is for O equals Fq Taylor series in Z, pi equals Z, for example, or 5Z, unless Q is 5. And if O is, say, ZP, then pi is P. That's the generator, a generator of the maximal ideal. Okay. So they form a basis of S, the circle of M. Yeah, so we just almost kill all of them. Yeah, we apply the uniformizer as many times as as possible. Then the next time will give 0. Okay, and this last before, well, next to last is not 0 but in the circle. Fine. So we order I as follows. We say j is less than I if j alpha j is lexicographically less than I alpha I. And now what shall I raise? Maybe theorem 2. No? Maybe the upper. We're almost done, but then we might have some fun, but there's almost no time left, so we'll have some fun on Friday. Okay, so we ordered I, and the subsets G in I are in bijection with compositions that are a little bit smaller than alpha, namely J corresponds to beta such that beta I is equal to alpha I minus 1 for I in J, and beta I is equal to alpha I for I in the complement. Then comparing definitions, we have d of j as defined there is equal to the distance between alpha and beta. And all the submodulus n in the circle of M of type 1 to the R have the same cotype. I mean, they are all conjugate under the automorphisms of M, so that they have the same cotype, namely mu, which was conjugate to beta. And there we are. This is the end of the long proof. Congratulations. Yes? Yes? The circle, so it's the union of all elementary submodules. It's a general mathematical notion. In any abelian category, the union of all irreducibles. Here, only erased the definition of a little bit smaller, yeah. But it was yeah, yes, I think so. Thank you. Thank you. Yeah, thank you. It was my mistake. Okay, and now corollary or exercise. I will give it in the next home assignment that the structure constant of this type equals q to n of lambda minus n of mu minus n of 1 to the r times the product. And here just count points in Grassmannian. And this will give us lambda I transposed minus lambda I plus 1 transposed, mu I transposed minus lambda I plus 1 transposed. And the Gaussian binomial coefficient is phi a of Q inverse over phi b of Q inverse phi a minus b of Q inverse. Since the Gaussian binomial coefficient like this is the number of points in Grassmannian over FQ and is the number of all points in the Schubert cells. Okay, but this will be in your home assignment. Okay, so that's the end of the proof, but now the time is up, and maybe we'll have no fun at all, but next time we'll start. I mean, this operation of a whole product is very closely related to operation of induction for finite groups. Like we had induction from Sm times Sn to Sm plus n. And this gave us, well, Frobenius product, which was just the usual product in the ring of symmetric functions, right? And here we have the whole algebra. On the one hand, it is just symmetric functions with scalar extended to polynomials in T. So essentially nothing happened. On the other hand, the natural basis is something interesting. It's a whole little with polynomials. And it corresponds to multiplication of induction from GL M FQ times GL N FQ to GL M plus N FQ. But certainly we have just block-wise subgroup like this. So it's M, N, M, N. This is GLM, this is GLN, and the whole thing is GL plus M. But that's not quite what I mean. I want a parabolic subgroup. So this will parabolic induction. And this parabolic induction will exactly correspond to the whole product. And I will explain it next time. So, I mean, from here, it's very close to the complete classification and computation of reducible characters of those general linear groups over a finite field. So we could do this, for example, but I already gave such a course last year, so I'm sick and tired of it, and I will don't repeat it. But we're almost there. We could complete the classification and computation of characters of these groups in March, if we wanted to. No, for Pleitism it would be GL M times N. Okay, but at least in the next time I'll explain that the whole product corresponds to this parabolic induction. Oh yes, there's a separate chapter, number 4 probably, or 5, I forgot. Everything about the characters of those finite Chevalier groups is in MacDonald. And say one funny thing is that, granted, what I'll explain next time, to go to the actual computation of characters, you need some trick with modularity, with finite characteristics. So we're only considering representations over complex numbers, but to actually succeed with this computation over complex numbers, you need to go to finite characteristic. Some Brouwer trick. Okay, thank you.